what I would like to do is just go over the example from the last lecture that perhaps I went over rather fast in the last 10 minutes, and it's quite straightforward, but I'll just do it for you on the board now. So what was the idea? So the idea was we were looking at a surface, and the surface was, I called it the fattened tetrahedron. So it looked something like the following. Sort of had 3 fingers coming down. So you can show that it's basically the same as the following surface. So it's like a torus with these sort of 3 prongs coming down onto it. So obviously the way I've drawn it, what I want to do is to split it into 2 bits there, one of which I'll call A. So let's call this bit A, and the toroidal bit here, call it B. So the whole thing, we'll say, is M, and we'll split it into these 2 bits. So what I want to do now is just look at these 2 bits. So we have A is, if we sort of pull it apart, we've got A is, and we stretch those sort of arms out, what we have is A is sort of like 3 tubes joined together, like this. And if you then stretch this, so you imagine it's 3 tubes joined together, this is homeomorphic to the sphere, but where we've taken 3, we've just poked 3 holes in it. Okay. And B then is, we look at what's left when we pull B off, what we have is a torus with 3 holes poked into it. Okay. So this is a sphere with 3 discs removed, and this is a torus with 3 discs removed. Okay. We're removing 3 discs from both of them. So open disc, so we've got the boundary of these things. So inside M, what is the intersection of A and B? Well, it's just three circles. So we've got A, over here, A union B is equal to the whole of M, and A intersects B is just 3 circles. The circle here, and the circle here. Okay. So what do we want to do? We want to work out the Euler characteristic of M. So by inclusion, exclusion, we have that the Euler characteristic of M is equal to the Euler characteristic of A plus the Euler characteristic of B minus the Euler characteristic of A intersects B. Okay, so let's just put this all together. So this is the Euler characteristic of a sphere. Oh, let's just shorten this. So that's S2, that's the sphere where we remove 3 discs, plus the Euler characteristic of the torus where we remove 3 discs, minus the Euler characteristic of 3 circles. Okay, and what we've seen before, so if we just take 3 circles, that's 3 times the Euler characteristic of 1 circle, but the Euler characteristic of the circle is equal to 0. So this whole thing is just equal to 0. So this is equal to 0. Okay. So the Euler characteristic of M is going to be the Euler characteristic of the sphere less 3 discs plus the Euler characteristic of the torus less 2 discs. So we just have to calculate these 2 things to see what's going on. Okay, so let me just erase a little bit now. What can we erase? So let's just erase this. So what I'm going to do is I'm going to claim that if x is a surface, then the Euler characteristic of x, where I remove n disks, and I really mean, I should say, when I say disk here, I mean open disks, so that I still have a compact manifold. So I just remove the interior of the disk, so we still have the boundary. The circle does lie on x, but don't worry too much about that. Is equal to chi of x minus n. Okay. So that's what I want to show. And this is just inclusion exclusion. So if we have chi, so if we just have x is that, by inclusion exclusion this is chi of x less n disks. Let me just draw this actually. So this is x, where I sort of just remove these disks. So that's x plus the Euler characteristic of these disks which I've just removed, the n, well there's n of them, and minus the intersection. And the intersection of those disks with x less the thing, so whether these intersect inside x, well they just intersect at circles. So this is just n, where we have circles here. Okay, so n circles. So this is the Euler characteristic of this plus n disks, so that's n times the Euler characteristic of a single disk, minus n times the Euler characteristic of a circle. So that's the Euler characteristic of the thing we're trying to find, where we've removed the disks, plus n minus n times 0, which is 0. And so we get the result we were trying to show. So this was that was the proof of the claim, and we just rearrange that, and we get the required result. So now what we can see, sorry, I'm not using my board space maybe as well as I might. What we can see is that we can now calculate these two bits. Okay, so let me just fill it in down here. You can obviously rewind on the video if you want to go and look back what I'm erasing. So this is chi of S2 less 3 disks. So that's chi of S2 minus 3 plus chi of the torus minus 3. So chi, the Euler characteristic of the sphere is 2 minus 3. The Euler characteristic of the torus is 0, so we get 0 minus 3, add it all together and we get minus 4. Okay. So we conclude that the Euler characteristic of M is minus 4. Okay, but that's not quite what we wanted to calculate. We wanted to work out what the genus of the surface was. So do that as follows. We know that the Euler characteristic is equal to 2 minus I've just gone blank for a second. The Euler characteristic is 2 minus the genus, 2 minus, the Euler characteristic is 2 minus twice the genus. So we have that the genus is 2 minus the Euler characteristic over 2. So we get 2 minus minus 4 all over 2 is equal to 3. So the genus of this surface is 3, so M is homeomorphic to M3, which is the three-hole version of the torus. Okay, and so that concludes the proof. Okay.